Hi everyone, welcome back to my number sense series. In this video, we're going to be talking about two different kinds of problems. One of them is relating to the triangle inequality, and one of them is relating to something called diagonals, and I'll explain each of them as they come up. So first of all, we'll start with what's on the thumbnail, a question relating to the triangle inequality, more specifically, isosceles triangles. Now, for those of you who don't know, isosceles triangles are triangles where exactly two of the side lengths, have the same length. So, for example, an isosceles triangle with two side lengths of 3 and 8. So you already know that two of the side lengths are 3 and 8. So the other side length must be either 3 or 8 because we already know two of the side lengths are the same and these two clearly aren't the same. So it's either 3, 8, 8 or 3, 3, 8. So we might imagine that they look something like this. But the problem is, number sense does not acknowledge that there's two possible triangles. They say the perimeter of an isosceles triangle with two side lengths of 3 and 8 is something. And if you find the perimeters of these, they're not the same, right? So what's going on? Well, the fact is, one of these triangles does not exist. Even though I can draw these and I can label the sides, the fact is one of these is drawn wrong. One of these has the wrong side lengths, right? One of these triangles does not exist. But why? Well, to understand that question, we have to look at the triangle inequality. The triangle inequality is something that says, for a triangle with side lengths A, B, and C, and let C be the longest side, we must have that A plus B is greater than C. In other words, let this be A, B, and C. No matter how you draw this triangle, it will always be true that the sum of two lengths is greater than the biggest length. A plus B is greater than C. So there are a few ways to explain why this is. One of them is a physical representation. Think of this as a rubber band, okay? A rubber band, stretched over two of your fingers, pull it like this, and then imagine pulling up that rubber band once. When you pull it up, you're kind of making a triangle, right? Imagine a rubber band that kind of looks like this, and you're pulling it up right here. Now this, when you pull it up, it creates tension, right? The rubber band is not meant to be stretched like that. So it must be that this is longer than this. The sum of these two lengths is greater than this. If you have to exert energy, you must be expanding the rubber band, right? Now, the second way of thinking about it is with geometry and formulas. So let me draw this. What I've done is split this in two, but if you know your geometry, you know that I just created two right triangles because this is a property of an isosceles triangle. When you draw this height, it creates two right triangles. And now we can look at this side versus this side, or this side versus this side, because we have a very, very famous theorem we use when we deal with right triangles called the Pythagorean theorem, which states a squared plus b squared equals c squared. And we don't have to exactly know what this means right now, but notice that c squared equals a squared plus something. In other words, c squared is greater than a squared. And since c and a are both positive, this means c is greater than a. In other words, the hypotenuse is the longest length. Some of you already knew that, but this is good to reiterate. The hypotenuse is the longest length. So this is greater than this. This is greater than this, and this is greater than this. Well, if this is greater than this, that means the sum of these two sides is also greater than this side, because you're basically just doubling each side. So that is the triangle inequality explained, and now hopefully you also see why one of these triangles is not real. This triangle, 3, 3, 8, how can this 3 be longer than this 4? We know that this length must be longer than this length, so this cannot be 3. This length must be greater than 4. However, this can exist. This is 1.5. We can definitely have 8 is greater than 1.5, and just verifying by the triangle inequality, the most basic condition, 8 plus 8 is greater than 3. Check. 8 plus 8 greater than 3. But here, 3 plus 3 equals 6 is not greater than 8. So this triangle does not exist, which is why we can say that there is definitely one perimeter only, which is 8 plus 8 plus 3, which is 19. Okay. Now, similarly, once you see one of these problems, you've seen them all. right? So let's just run through this one real quick. The perimeter of an isosceles triangle with the side lengths 5 and 11 is, well, I mean, just like the last video, we saw that it's either 5, 5, 11, or 5, 11, 11. But when you see this, you should automatically be suspicious. 5 and 5 are too small to make an 11. 5 plus 5 is less than 11, so this triangle does not exist, and so it must be a 5, 11, 11 triangle. So the perimeter would be 27, just adding them all up. So that's the first kind of problem. The problem where it seems like there's two triangles because they tell you it's isosceles, but in actuality, there is only one because one of them does not exist. Great. Now onto the second kind of problem. In this video, we are doing two kinds of problems because really there's not enough variation between the two, and it's really just understanding one problem and then you understand all of them. So we are putting these two in the same video. Now the second kind of problem has to do with something called a diagonal. In case you don't know, and I don't expect you to at all, let's draw a shape out, and I'll show you what a diagonal is. Now, of course, we know that these are called sides, right? But sides are connecting two adjacent vertices. But what if we connect two other vertices, like this, or this, or this? These three are making us lengths that are inside the shape. They are called diagonals. A diagonal is formed when you connect one vertex to another one, and that one passes through the interior of the shape rather than being like a side length or something. And a very, very common question that NumberSlings is going to ask you is, how many diagonals does the shape have? And, of course, the only thing that's going to matter here is the side length, is how many sides it has, because they're going to tell you that it's a regular shape. And a regular shape is a shape where all the side lengths are the same and all the angles are the same. So you only have to worry about how many sides there are. So how do you figure out how many diagonals there are? Well, let's think about it. 1, 2, 3. Okay, let's go to another vertex. Let's draw 1, 2, 3. Let's go here. Let's draw 1, 2, 3. Go here 1, 2, 3. 1, 2, 3. 1, 2, 3. We've drawn all the diagonals, and how many are there? Well, if you count them, you'll just know that there is 9. But we are not going to count them every time because we can do something much more intelligent, multiplying. See, a diagonal is formed by two vertices, right? So all we have to really do is choose our two vertices to make the diagonal with. So we might imagine that our diagonal can start on any vertex, right? Any vertex. How many choices are there for our first vertex? Well, it's any vertex, so it's 6. 6 times the amount of choices there are for the second vertex. How many choices are there? Well, we can't choose the same vertex because then our line segment isn't going anywhere. But also know that if we choose the vertex or this vertex, the two vertices that are next to our starting vertex, it actually just makes a side, and that's not a diagonal. So we can't choose those two either. So it's going to be 6 times 3. But 6 times 3 isn't 19. What? Isn't 9, sorry. 6 times 3 isn't 9. Well, it isn't 19 either, but it's definitely not 9. So we've done something wrong. And what did we do wrong? Well, take this for example. If we start with this vertex and we attempt to draw it to another vertex, for example here, this makes a diagonal, yeah? But if we try to start from this vertex and draw to this vertex, we've made the same diagonal. In our multiplication, we've overcounted. We've counted the same diagonal twice. Every diagonal, in fact, has been counted twice. So what we should do is divide by 2, right? And this will give us 9. And this is how you generally find the number of diagonals. And if you found that confusing, hopefully what I will show you next can help to alleviate that. So let's do this with an octagon. An octagon, once again, let's see how we can choose our diagonals. Once again, to make a diagonal, we need two vertices. So let's choose this vertex. This is our starting vertex. Let's see how many times we can draw it. 1, 2, 3, 4, 5. There are 5 options to go from this one vertex. And so if there's 8 possible starting vertices, we can start from any vertex. And we can go to 5 other vertices. And remember, this diagonal, where you start here and end here, is the same as starting here and ending here. The starting and the ending doesn't matter because they create the same diagonal, the same side length, right? So we have to divide by 2 because if we multiply just doing that, we actually count every diagonal twice, starting here, ending here, or starting here, ending here. So 8 times 5 over 2 is going to be 20 diagonals. Of course, we can also generalize this because there is a formula. And that formula, hopefully if you understood this, should be very easy. Because that formula is just going to be, given n sides, it's going to be our starting vertices, n, and then times how many choices are there for our second vertex. Well, once again, it would be n, but we have to subtract some that are definitely invalid, right? We can't have the same vertice, we can't have the same vertex, that's -1, and we can't have any of the two vertices bordering it, because that would just make a side, not a diagonal. So it can't be 1, 2, 3. We lose 3 choices, so it can be n minus 3 choices. And then finally at the end, we've overcounted, as we see, so you have to divide by 2. And this is our formula for the number of diagonals that a certain shape with n sides has. So all you have to do is apply this formula to our next problem. The number of diagonals in a regular dodecagon is blank. Once again, hopefully we remember what a dodecagon is. This is the longest shape that Number Sense will expect you to memorize, so I decided to test it again. A dodecagon, do meaning 2 and deca meaning 10, has 12 sides. 2 plus 10, 12 sides. So how many diagonals does it have? Let's just plug it into the formula. It's 12 times 12 minus 3 is 9 over 2 is 54. And that's all there is to it. So in this video, we covered 2 different kinds of problems. One about isosceles triangles using the triangle inequality, and one about diagonals in regular shapes using some basic combinatorics. Now, if you didn't understand the math I did in this video, I want you to come away from this video with 2 things. Please try to understand at least these 2 things. The first thing is the triangle inequality. A plus b is greater than c. This statement right here, should have boxed it. A plus b is greater than c. The sum of any 2 lengths in a triangle is greater than the third length. The second thing I want you to remember from this video is this formula, n times n minus 3 over 2. Of course, it's much better if you can understand why the formula is this way and where it comes from. But if it is really a struggle for you, if you really just don't think you can understand it right now, that's fine. Just memorize the formula, n times n minus 3 over 2, and remember, that is how many diagonals there are in a shape with n sides. So, I hope this was really helpful to you guys. That's going to be it for today, and thank you for watching, and I'll see you next time.